Hello there, it's been a while since I recorded any videos on my YouTube channel, especially understanding the system series. Now I'm back at it with a new video, very important one, and as you can guess from the title and the whiteboard behind me, because that's our educational material. I apologize, I don't really have much time to create educational material or edit the video, but I hope this video is going to be high quality of the information in it and the experience that I think I have and I put into such a videos. So as we said, the video today is going to be about real-time systems and application. So what is real-time systems and application? Well, the practical definition says real-time systems are computing systems where the correctness of operation depends not only on the logical accuracy of the computations but also on the time at which results are produced. Missing a deadline, you see, this is in my opinion the most important thing. Missing a deadline, which help you solidify the idea of real time systems within your head. Missing a deadline can lead to system failure, making timing as critical as functionality, and that's what sets real-time systems and applications apart of anything else you ever know as a software engineer, right? And the thing we can take from this practical definition is we need to remember this picture right here. You see, functionality and timing. It's not only now the functionality is critical and should be accurate, but also the timing of that functionality should be guaranteed and accurate, right? Which brings us to the next topic. What is the timing we're talking about? I hope you understand this well. I'm gonna give you an example to solidify this idea. What do we mean by saying timing? Basically, when we say timing, within the hardware, our software, within the hardware, right, there is a ticking clock, right? And that clock will allows us to determine how long this operation took, right? In milliseconds or even nanoseconds. The CPU clock, as far as I remember, it's been a while since my computer engineering degree. I think it's in nanoseconds or time smaller than that, right? Or the frequency and so on. And the way we determine what kind of real-time application we are building, well, we need to decide, is our application needs hard real-time or soft real-time? Hard real-time or soft real-time? Because they are very different. What the difference between them? Again, timing, right? Because with hard real-time, missing a deadline, right, of an operation is catastrophic. It's disastrous, right? To give you an example, as you can see right here, it says airbag deployment, peacemakers, anti-clock braking systems, and so on. For example, let's take the airbag system. I'm going to do an educated guess. I never worked on cars, right? But here we have the airbag system, right? And this airbag system within a car, and this is right here oh, I cannot spell accident. This is the accident where the accident is about to happen. So we have the car right here, and just before the accident happened, in milliseconds, right? Does it need to be that accurate? Yes, of course. An airbag system with the seat belt is life-saving mechanism. Always put your seat belt on, right? Even if you riding in low speed streets, always put your seat belt on. Why? Because it's gonna save your life. That's the bottom line, right? So back to here, the airbag system need to deploy at really specific time. Why I'm making this educated guess? Because if you think about the functionality of an airbag system, what it need to do or its purpose is to absorb the impact, right? Newton first law. For every reaction there is a reaction. So you have this massive energy coming at that person that drive the car, right? And that airbag system need to time its airbag deployment right when the impact happens. So it absorbs that massive reaction that coming at that person to, of course, to keep him in seat. That's the seat belt, right? Does it also the airbag prevent his head from hitting left or right or the front hitting something hard and damaging the fighter area. And that's what we mean by hard time. So if the airbag system here missed the deployment of the airbag with uh, with uh, a margin of accuracy that's really bad, this is catastrophic, right? If we manufacturing a car and we want to uh, send this car in production and we haven't spent enough time, say like, yeah, it's okay, just put it in production, let's ship, right? It's going to be really bad if we like afraid of uh, losing sales when this car goes into the market and has a failing airbag system. The first accident that that car have is a game over for the entire company, right? So that's what do you mean by hard real time, right? The timing need to be very very accurate, and the opposite of it is soft real time, or how consulting companies like to promote it to their clients, near real time, and some fancy words, but all of them mean that all of them mean soft real time. Soft real time, it's miss and soft real time missing occasional deadlines degrade the performance, right? But isn't catastrophic, right? Take Twitch streaming for example. When you go watch your favorite gamers play the video games, and you're watching that video game and the performance degrade, right? It's not that catastrophic, right? Your internet is slow, right? That the Twitch stream itself has just got a lot of people, whatever that is not catastrophic, right? The performance is gonna degrade. You're gonna see screen acting strangely, but no one cares. Life moves on, right? And that's the difference between hard real time and soft real time. And that's how you decide what kind of system or application you are building. With hard real time, usually the hardware itself need to be optimized. For example, if I could remember in university we were doing a lot of work with microcontrollers that have ARM processors. ARM processors within them there is real time guarantee of hard real time, right? And those microprocessors you can program them to do a specific task. For example, I can put a microcontroller on my balcony, and whenever it starts raining, like weather forecasting, but real-time weather forecasting, whenever it starts raining I want to be notified on mobile. So that's on the embedded system, right? This is a combination of both actually, soft real time and hard real time. On the on the microcontroller itself, the sensor, right, need the sensor, both software and hardware, need to be optimized for hard real time, right? Whenever the first whenever it senses humidity or whatever that is, right, it's going to send what, a notification. The software is the functionality software that runs on the microcontroller, right, is going to be of two parts. The first part is the sensoring logic, which is tightly coupled to timing, and the second part is the API or whatever that is that I'm planning to push notification on so I can see it on my mobile. You see that? That's amazing, right? And as we said, in hard real time is totally different than soft real time. Soft real time application, you can build them on your old PC that you don't use anymore, right? You can transform it into server and you can start streaming. You can use it as a streaming service. You can power on it Plex, for example. Plex is great software for watching movie and putting all of your content, right? Movie content, and that's the difference. Do you understand now the difference between soft real time and hard real time? Because it's really important, right? As we said, in hard real time you need the hardware to be optimized, built for hard real time. The software itself, for example, here you need to use C. Why C? Or VHDL or whatever that is, because VHDL is different programming languages for FPGAs, if I can recall from the university days. But with microcontrollers, we usually program them with C. Why? Because C is a high level programming language. Why is high level programming? Because you can read it. It's not assembly, right? It's not as assembly code. If you showed the assembly code to TypeScript or JavaScript programmer, which is me currently, so who cares, right? I still do C++. Um, they're gonna panic. I still can read assembly, work with assembly, no problem, right? I need to refresh my mind about assembly language, but they are totally different. When you compare C code to C plus um, JavaScript code is totally different. It looks different, right? Why it looks different? Because as high-level programming language, the closest to the hardware, right, is C++ or C. C is a superset of C++. C is the closest you can get as a high-level programming language to the hardware, right? And that's why they call it the mother of all programming language. So that's all about hard real time, soft real time. So when you're building analytic a dashboard, for example, this is a real-time application. If it's required to be a real-time application, you consider it on interval and still like it's soft real-time. It's on the far spectrum of soft real-time, but still a real-time application, right? And that's why, because the only difference is it like soft real-time or it's soft real-time. The only difference is the timing, right? I can put my analytic dashboard to be on a ticks, right? Every tick is take 1 second, and the screen is going to update. One example on this, I remember I attended this week. I attended a free webinar, and the presenter had something really nice on the screen, on the meeting. So one of the the activities of that webinar, people started typing some words, right? And that word was going to appear on the word cloud. Let me show you what a word cloud is. Word cloud is this right here, right? So while people typing on the stream, the words start to move beautifully. See, the data word gets a bit bigger, the inside word gets smaller, and that's based on the people, how the people type. So if we just done like millisecond soft real time, this visualization will look ugly, will look very ugly, right? Nobody gonna look. It's like, what is they doing on the stream? What is this? Is that kind of black magic? Nobody gonna get to see what word exactly the people are interacting with, right? So in the soft real time, we're gonna say no. We need to make the scheduling of this real time to be 1 second per tick. Why? Because it's gonna make the visualization beautiful. And that's how you develop real time applications. You need to decide, okay, what exactly we are building. Are we building a microwave software, right? When we click the button, we need in milliseconds, nanoseconds, like your eyes cannot catch. When you click the minute button, it appears on the screen 1 minute. or we are building some kind of streaming services or audio processing or whatever that is, and that's you distinguish. And that's really good point we mentioned a few moments ago. um, when you decide between hard real time and soft real time, the way you do that is just say, is my application is related to the physical world or not? If it is, then you must be leaning more on hard real time. And with the IoT architecture and whatever that is, you're gonna start distinguish your context boundary. You say, okay, this part of the system is gonna be soft real time, and this part of the system is gonna be hard real time, and so on. And you do all of that through what? Scheduling. Even the hardware, even your processor. You see, your processor architecture is all about scheduling. But wait, how hard real time processors are hard real time if they do scheduling? Well, they guarantee you they guarantee you uh, for a specific operation a specific timing, right? And that's the whole idea. We spend a lot of time here because it's very important to distinguish between hard real time, soft real time, and we're going to move forward now. And for all real-time systems and application, we have key characteristics. The first one is determinism. We're not talking about here about the logic, right? If you building some embedded system, right, make sure your logic is deterministic 100%, please, right? Please make it sure it's deterministic 100% for that embedded system, because we don't want any probability going there, right? And here we're not talking about so much when deterministic on the functionality. We're talking about the response time with hard with real-time systems and application. The response time need to be guaranteed to our user. So if you are a consulting companies and we're creating some kind of near real-time analytic dashboard, right? We need to give them the framing, right? Not necessarily consulting company. Let's take the GPUs for example. When a GPU is to understand the missing, that's a really good example. When a new GPU come out to the market, right? And during the show, they will put the game on a specific setting, and they start playing the games. And up top, you see frame per second. That's soft real time, right? Soft real time, right? It's soft real time for the game, right? Soft real time for the game. That's how we're gonna make the distinguish. That's soft real time for the game, playing the game, but hard real time on what? On the GPU itself, right? Because you need to run specific benchmark on the GPU to determine the actual hard real time frame per second. There is so many of them. But back to our example, when you take that GPU, you just get to start, oh, I want to play that game with plus 50. You have the money, of course, and you just say like, oh, I don't mind 1000 watts GPU. I want to play this game with 50 more frames per second, right? And you go buy that GPU and install it on your PC, and you start playing, and you're surprised. What's going on here? Why I don't have the same? Oh, they lied to me. Oh, they're scamming me. The GPU company is scamming me. No, the GPU company is not scamming you. You don't know anything about hardware, right? Because what happened, if that's the case, your CPU timing, right? To make it simple, your CPU performance is bottlenecked your GPU, right? Or vice versa. It happens sometimes. Because why this bottleneck happen? Because the timing of your GPU is much faster, right, than the timing of your CPU, and that's what causes the bottleneck. So you upgrade the CPU and say, oh, yeah. They didn't scam me. I'm the scam. Okay, back to the topic. So now we understand what determinism is, right? We need to guarantee specific response time to our clients. So whatever that application we are developing, whether it's hard real time or soft real time. And with scheduling, with another key characteristic for real-time application is scheduling. We need to allocate, and so scheduling means basically we allocating CPU time to meet deadline for tasks. So we have task A, task B, task C, whatever that task is, and they all go into the CPU, right? We need some kind of scheduling algorithm there. We're going to talk about scheduling algorithms to determine which task to run first, right? And there is different type of scheduling algorithm, and I'm going to mention them. And the fourth thing is concurrency as well, parallelism. This is very important. A lot of software engineers don't know what is the difference between concurrency and parallelism. So for concurrency, let's put this so you never forget it again. So we have two CPUs. Up top we have one CPU, right? Here we have two CPUs. With parallelism or multi-threading, first of all, what is a CPU? So it's not that physical thing within your computer. No, this is your central processing. This is microprocessor. Actually, it's your central. No, this is your central. This is your processor. Your central processing unit. Within that central processing unit, there is multiple microprocessors, right? And each of them can run tasks on their own, right? And for each core, so for example Intel I whatever that 5 whatever that is, I don't recall the model, 13400, one of the best gaming CPU out there at that time, budget friendly. It had 8 cores, right? It had 4 cores, right? And what that mean, 4 core, that within every core there is two CPUs, right? That's what we mean by CPU. So with multi-threading or parallelism in programming, you actually running tasks on different CPUs right here, right? Task 1. Let's change the color. This looks ugly. Back to black. Right there. See, that's basically parallelism, right? With concurrency, on the other hand, you have one single CPU, but you're gonna spawn two different processes, right? On each process, what you can do is you can run tasks you can run tasks concurrently. See, I just got confused between parallelism and concurrency, and that's the whole difference between parallelism and concurrency, right? And there is other things like context and race condition and very important things to distinguish between how to handle them in concurrency and multiprocessing or multi-threading, but we're not going to discuss that for this video. And that's concurrency, this key characteristic within real-time system. And here what we basically want to do is we want to our real-time system need to be either can execute tasks in parallel way or concurrent way. Didn't put parallel here, but that's the point. And three more things to really understand with the real system, a real-time system or real-time application is latency, right? Latency basically is the time between stimulus and response. In hard real-time applications, that will be the sensor. When the sensor receives, for example, humidity signal, what it's gonna do is gonna send a signal within that microcontroller, right? And based on the logic, there's gonna be a response time, right? Based on that stimulus, in that case humidity, and the response of that sensor. And how this is hard real time, right? And soft real time, for example, when someone click on the stream in Twitch, the moment they hear that streamer talk and the moment between their click on that streamer stream and they start to hear the streamer talk, that's the latency for that specific user. And Twitch is a great software solution. Their engineering blogs is out there. And of course they have content delivery network and they have optimized solution, but sometimes based on the hardware of the user, the network, the internet speed of the user, where they live, and so on, there's going to be a latency. And that latency, what is it? The time between stimulate and the response for both hard real time and soft real time. Another thing very important is the throughput, the amount of data processed at the period of time. Let's to understand throughput from hard real time, because it's really easy to understand it from soft real time. Like for example, like your web application, how many requests per second, right? This is the throughput, right? How many users can handle the for 1 hour and so on, right? That's the throughput, right? And the throughput, the practical definition for it is the amount of data processed at period of time. And one thing a lot of software engineers do not know about is Jitter, because not that many software engineers in their career have done all types of performance testing. I did because I worked as test software engineer for a whole year, right, during my career. And there I had the opportunity, even before I am really, I really like performance. I really like performance and optimization, right? And that's why I program in TypeScript. No, I'm joking. JavaScript is a great programming language. It has some issues, right? But overall, for its purpose, is a really great programming, especially TypeScript. TypeScript is just in the Matrix movie is the tuple dynamic programming language. The tuple. Where is it? Did you eat both? This meme. This one right here. Right here, you see? This is Java dynamically typed programming language and type-safe programming language, and this is the TypeScript programmer. Did you just take both of them? Yes, why not? Back to the main topic, Jitter is a really important thing because as I said, I worked on performance testing, and Jitter basically is variation response time. When did I see this concept in practice? Basically, when you do spike load testing, right? The difference between stress load. Let's just give example about performance testing is a really important thing to know. So in load is stress load test, you just want to know the maximum amount of users your application can handle, right? Because when you reach that specific threshold, your latency start to degrade or your software start to error out, right? And that's stress load testing. For example, for a database, for one CPU, right, instance, that database is running, how many query per second we can run, and so on. Jitter, on the other hand, where did I notice this concept? When we do spike testing, right? With spike testing, right? What you're doing basically, for example, you go 100 users right here, and then for a period of time you go 500 users, right? And just go back to 100 users, and then again 500 users, and so on. What I notice is like uh, f- uh, for that period, when we increase the load, decrease the load, there is a jitter. Of course, there is a jitter, right? But the jitter, the pattern repeats where when the loads goes down, right? When the loads go down and calm down, the response is different. That's one of the systems that I spark test. So we talked about very important things so far. Now, what is the other thing we need to understand? We can talk about each one of them in details, right? But I think they are like self-explanatory. We explain them well. We give example on concurrency, and I think the one only thing for you it's really hard to understand is scheduling, especially when we say like allocating CPU time to meet a deadline. What do we mean by that? We explained it. We have many tasks, right? For example, Node.js event loop, right? within that event loop you're gonna have micro tasks, right? And the purpose of the event loop um, to have this callback stacks right there, and just the event loop is going to take from them callbacks and just execute them, right? And in order for you to create something like that, a scheduling solution, whether it's on the software part of things or on the hardware part of things, there is some specific scheduling algorithms, right? And the most famous scheduling algorithms, there are two. The first one is rate monotonic scheduling, RMS, and the second one is earliest deadline first. So the first one is RMS and the second one is EDF. The first one, static priority assignment. um, the static priority assignment rate monotonic scheduling is basically static priority assignment where task with shorter period gets higher priorities, and that type of scheduling algorithm is optimal for fixed priority scheduling. What do you mean by that? So let's see at this diagram right here. We have two tasks, right? The first one's gonna take execution time is just 1 second, and the second one is gonna take 3 seconds. So which one we gonna pick? Which one gets the first priority? The yellow one or the blue one? Based on how rate monotonic scheduling design and guarantee, we're gonna pick the blue one. We're gonna give it priority 1, and the other task is gonna get what, priority 2. Why is that? Because we are optimizing for fixed priority, right? So if you have a system like the CPU, or like ARM processors, right? Most of the hard real-time CPUs I worked with in college and even in internships were ARM processors, and those processors basically their guarantee of real time is really small, on nanoseconds, right? Nanosecond per tick, or I don't remember anymore the technical terms, but let's just say tick, right? And here you have the tick is here is 1 second, right? This is just like 1 nanosecond, right? And we have two tasks. One of them takes 1 second, and the other one takes 3 seconds, right? Why you choose RMS for the system we're designing? Because the tasks that's going to be run and executed is going to be what, predictable at fixed duration, right? On the other hand, when we need a bit of flexibility, right, and we need so that's why RMS is really great for periodic tasks, right? Most of your periodic solution cron jobs software that you use, they implement some kind of rate monotonic scheduling of some kind, right? On the other hand, we need something more dynamic where 100% utilization is wanted, desired, right? In that case, we're gonna go with earliest deadline first, right? EDF. And EDF is dynamic priority assignment where the task with the nearest deadline gets the highest priority, right? Optimal for unpredictable workloads where 100% of utilization is preferred. Now we have two tasks in front of us, right? The first one is the execution time is 5 seconds, but the deadline, right, is in 2 seconds. We need this task to be over in 2 nanoseconds. We need this task to be over in 2 nanoseconds, right? The execution time is 5 nanoseconds, and the deadline is 2 nanoseconds. Based on the EDF, it says like, okay, this task is going to execute first, and that's how EDF as an algorithm can schedule things dynamically. How? Based on prioritization based on deadline, right? That's some of scheduling algorithms, and that's it. To be honest with you, the most important things, in my opinion, to know about real-time systems, right? Now, if you wanna understand real-time systems better, here is some hands-on projects, right, to implement takes you from a beginner with real-time system to an expert. Yes. And the first one, just implement some kind of event logger, right? With time constraint. So you're going to build a system that logs events with guarantee maximum latency, accepts event from multiple sources, guarantee logging within 10 milliseconds, implement circle buffer for log free writing, track missed deadlines, right? And here what you're gonna understand, so you're gonna start understand many things. The first one is deadline tracking and basic scheduling. You're gonna implement some kind of scheduling there, and you're gonna manage buffering. And buffering is very important when you implement in every single scheduling algorithm out there. The second thing, right, here, and this will allow you to do the to advance to the next project, which is going to take you a week to implement, right? If you're beginning in real-time application. So what I want you to do is create a multi-threaded sensor fusion system. So what you're going to do basically simulate an IoT device with multiple sensors, right? You don't need the sensors itself, so, right? Nor the hardware. You're a software engineer. You're not expected to understand embedded systems. But if you want, that's okay. But what I want you to do is just create a simulation of multiple IoT devices, right? Multiple IoT sensors. And here, what you want to do is for 3 to 5 periodic sensor with 3 to 5 periodic sensor tasks with different rates, right? What we mean by here is just we're gonna get the timing right, get that understand that hard real-time, soft real-time systems in general care a lot about timing, right? As we said in the top, it's both functionality and what timing that matters. And here what you want to do is just do some kind of real-time data fusion algorithm. What we mean by that is you want to have your buffers right ready, and based on a tick you want to take all of that data and transform them to some kind of another data, right? And here you can use if my memory helps me, map and reduce, for example, map and reduce technique and so on. And here what I want you to do is do not use the library, just implement the priority based scheduling. You can use priority based queue, right, data structure, and you can implement that easily. And what you want to do here as well, add watchdog timer for fault detection, right? When your timing goes off during this simulation, I want you to detect the faults or the errors. Here, what you're going to learn basically, you're going to learn periodic tasks, priority scheduling, and timing analysis, right? Great. So here we have the third and the fourth project. I'm just going to put them on the screen. And those projects as well advance and solidify everything you learned in this video. The third project is going to be soft real-time media processor, and the second one is going to be a hard real-time control system, and the fifth one is autonomous vehicle subsystem, right? Here you're going to implement a BID controller for a simulated system. Going to create a lot of simulations, but you can, I don't want you to go to jump into the hardware if you really liked this video, but I want you to implement many simulations, and those simulations are going to help you to do what? To do great, right? To do great when you decide to transition to real hard time. Because back in college, most of my internships and even a job for a year, it was mostly with hardware, right? It was mostly with hardware. Some of them were just internship. Some of them were just IT with networking. But I also worked on with thermal printer distributor, and I was fixing and checking the firmware and updating it and even reading the code. They allowed me to read the code and suggest for them optimization if they wanted. So here we have really good projects to help you solidify wherever you learned today. I hope you learned a lot. And that's all for this video in the series of understanding the system. More to come inshallah in the future. To that time, see you.